I'm just creating this video because let's say that you don't understand the lesson. Then you can go back to this video and watch this video as many times as needed in order to understand how the different trends they behave across periods and groups. And it's very important that you understand how these trends behave, because otherwise you're not going to be able to understand anything about bonding. The first trend that we're going to analyze is the atomic radius. And as you can see over here, it is defined as half the distance between the adjacent nuclei in a crystal of the element. Do you understand that? I don't understand that. That's why over here I was putting another definition so you can understand this concept better. In other words, what is the atomic radius? It is the distance from the center of the nucleus of an atom all the way to the boundary of the electron cloud, all the way through the last level of energy in there. How is the atomic radius behaving in a group? And for example, over here we have potassium. Potassium is located in group 1, period 4. And you know that because over here you have the electron configuration. The atomic number of potassium is 19. So in the nucleus, you're going to find 19 protons. In a regular nucleus or regular atoms, you're going to find 19 neutrons. And then you have 19 electrons that you have to organize in the electron cloud. When you write the electron configuration for potassium, see the distance from the center of the nucleus all the way through the last level of energy, that's the atomic radius. Okay, miramos, what are you using that example? Because if you look over here, see, down here, rubidium is also located in group 1. Okay, see, down, potassium. You look over here at the periodic table, you have potassium, see, with atomic number equal to 19, and then you have rubidium. Why am I using these two? Because I want you to explain the trend of the atomic radius in a group. So down a group, what's gonna happen? See, the atomic number of rubidium is 37, meaning that you have to organize 37 electrons in the cloud. See the difference between potassium and rubidium when you are down a group. So center of the nucleus all the way through level number 4. Center of the nucleus all the way through level number 5. And that's why when you are moving, see, down a group, the atomic radius is gonna increase. Why the atomic radius is gonna increase? Because the level of energy, they are increasing as well. Okay? The level of energy, they are increasing as well. Now, remember what's gonna happen in a period. I'm gonna let you know right now. In a period, what's gonna happen in a period? You know that's elements that are in the same period. Elements that are in the same period, they have the same level of energy. For example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, all of them, they have 2 levels of energy. Okay? And that's the information that you can get from the period number. The principal quantum number, the last level of energy when you are organizing the electrons following the electron configuration. Okay, so what I'm doing this because remember now I'm going to explain the trend of the atomic radius across the period. So I'm going to start with lithium. Lithium has an atomic number equal to 3. Okay, 3 protons, as I was explaining before. No radioactive, see, you don't have an isotope of it. Bueno, you have one of the isotopes over here with 3 neutrons, and then you have to organize the electrons in the electron cloud. The distance from the center of the nucleus all the way through the last level of energy, that's the atomic radius. Okay, remember what's gonna happen, because as you were saying before, let's say that you have another element from the group, they're gonna have the same level of energy at the end in the electron configuration. And you're right, I'm using oxygen over here, and as you can see, oxygen is located on period 2 as lithium. But what is the difference between lithium and oxygen. As you can see over here in the nucleus, when you go from left all the way to right, see, the atomic number is gonna increase by 1, see, left to right. When you go from left all the way to right, the atomic number is gonna increase by 1. However, the nucleus is gonna grow faster, see, or it's gonna increase in size faster than the different level of energy. Why? Because in addition to the one proton that is gonna increase, you have another neutron in there. Since you have the you have the same level of energy and the nucleus is increasing faster than the level of energy, the attraction between that nucleus and the electron is gonna increase, decreasing the atomic radius. Okay, so when you go across the period, even though the atomic number is increasing, because the nucleus is growing faster, you have more subatomic particles in there. It is gonna attract the electron close to the nucleus. The atomic radius is gonna decrease across the period. And you have that trend explained over here. See? When you go from left to right in the periodic table, due to an increase of the number of protons in the nucleus and the fact that the principal level of energy stays the same, the atomic radius is going to decrease because it's going to be the increasing protons, but at the same time, then you have neutrons inside. That's going to make, that distance smaller because there's going to be more attraction. Now we have over here the second trend that we're going to analyze. The second trend that we're going to analyze is the Ionic Radius. Okay? The Ionic Radius, according to the definition that I have over here, is the measure of an atom ions in a crystal lattice. Do you understand that? Don't get that. That's why I was putting over here another definition. In other words, it is the distance from the nucleus to the boundary of the electron cloud, see, to the last level of energy after the atoms, they have gained or lost electrons. Mirama, pero who's going to gain, who's going to lose electrons? So that the tendency of the metals is just to lose electrons. See, later you will know why. Okay, but the metals, all the metals, they're going to be losing electrons. It's a rule. Or it's the behavior. Okay, the non-metals, they are going to gain electrons. Okay, why the metals, they are going to be losing electrons? The question, okay, the answer is simple. I'm going to start over here with lithium. Okay, lithium. And it has to do with the Octa Rule. Remember that the Octa Rule is the tendency of the elements just to reach stability, chemical stability, by completing the last level of energy following the noble gas configuration. Lithium has an atomic number equal to 3. Okay? So that means that lithium has 3 protons, 3 neutrons, 3 electrons that you have to organize. So you have 2 in the first level. In the s orbital, then you have only 1. Okay, but when you look at lithium is over here in period 2. In period 2. So the noble gas that you have here at the end is neon with an atomic number equal to 10. In order for lithium to reach chemical stability, okay, lithium needs to complete this, the s and the p orbital of the second level with all the electrons. And I have a question for you. Is easy for lithium just to lose that 1 electron or to gain 7? Another one for the S and the C for the P. So, which process will take less energy in order for lithium to reach the electron configuration of neon, or to reach the electron configuration of any noble gas? It's going to be easy for lithium to accept 7, but just to lose 1. See? Losing one is taking less energy. That's why lithium is going to lose one electron, and instead of reaching the electron configuration of neon, it's going to reach the electron configuration of helium, which is another noble gas. That's why the metals, they tend to lose electrons, because it's easy for them to reach the electron configuration of the noble gas on the period before than to accept more electrons than the one that they have to lose. But Ramos, what are you doing all of this? Because I want you to see the trend let me see, what do I have here? I have the trend in a period here. As you can see, okay, lithium is gonna lose one electron just to reach the electron configuration of helium, and the second level is gonna disappear. Well, it's not gonna disappear, because remember that matter cannot be created, destroyed, only transformed. But it's going to another place. You will know where place is going. Okay? So the second level of energy is gonna disappear. Now the distance from the center of the nucleus to the last level of energy has been reduced. Consequently, the ionic radius, when it's gonna be like a smaller. When lithium goes from an element to a positive ion, the ionic radius is gonna be smaller. Following that same analysis, see, that's lithium, I'm gonna move in the same period. So I'm gonna move from lithium all the way through boron over here. Okay. So, and I have boron over here with atomic number equal to 5. And I'm gonna follow the same. My protons, my neutrons, my 5 electrons organized in the cloud. But then I have a problem. So in the second level of energy, in order to be chemically stable, they need on the last level of energy 8 electrons, because that's how they reach the noble gas configuration. Over here, in the last level of energy, do you have 8 electrons? When you add 2 plus 1, then you have 3. And then you have to ask yourself, you're going to ask yourself, is it easy for boron to lose the 3 or to accept the 5? Of course, that losing 3 is going to take less energy. But careful with that, because when you look at the periodic table, okay, boron is a metalloid. So in the case of boron can lose the 3 or can accept the 5. But for now, we're going to assume that is losing the 3 electron is going to take less energy. So when boron is doing that, what's going to happen to the atomic radius? It's going to decrease. So yes, when you move across the period, the tendency within, I want to clarify this, the tendency within the metals is just to the ionic radius to get smaller. Because if you look over here on the periodic table, sodium is going to lose 1 electron. Magnesium is going to lose 2 electrons. But if you move over here to aluminum, which is a metal, it's going to lose 3 electrons. See that? So the more that you move from left to the right within the metals, the smaller that the ionic radius becomes, because the metals, they are losing more electrons. Now, what is the catch in here? That at some point, you're going to reach the non-metal part. See? You're going to reach the non-metal part. You're going to start over here with nitrogen, because it's the same process. Okay? Same process. Atomic number equal to 7, and you're going to distribute that in your electron configuration. In order to become chemically stable, that's the Octa Rule. Elements, they need a electron in the last level of energy. One more time. That's how they reach the noble gas configuration. See? But nitrogen, when you count the electrons here on the last level of energy, 5. You have to ask yourself, which process will take less energy? Okay, accepting 3 or losing 5? Use your common sense. And that's why the non-metals, they're going to start accepting electrons. because by accepting electrons, they're going to be able to reach the electron configuration of the lower gases using less energy. Is that what happened with the nonmetals? Now, in this case, nitrogen was accepting 3 electrons. Okay, let's do the math. Okay, so now you have 7 protons in the nucleus, plus, but now you don't have 7 electrons, because you were nitrogen, nitrogen was accepting 3 more, and if you count that over here, you have 2 plus 2 plus 6, that's 10 electrons that are negative. If you know how to work with integers, you know that plus 7, which are the protons, minus 10, which are the electrons, that is equal to negative 3. So when nitrogen is accepting 3 electrons to reach stability or chemical stability, it's going to get a charge equal to negative 3. It's a negative ion. See? The metals, they were losing electrons, so the atomic radius is going to decrease. But all of a sudden, when you are moving to the metal, the non-metal part, all of a sudden, the non-metal, they're going to start accepting electrons. So this distance from the center all the way to the last level of energy is going to increase. Meaning that it's going to increase or keep increasing when you move within the non-metals. No way, Jose. Why not? And I have the example over here. So now you are going to move across the period, but you have this non-metal, which is fluorine. Atomic number equal to 9. And I was explaining at the beginning that the atomic or the ionic, I was explaining that the nonmetals, the tendency of the nonmetal is just to accept electrons. Look over here to the electron configuration. One more time. It's gonna be easy for fluorine to let go 7 or to accept 1. That's what is gonna happen in nature. Now doing the math, now you have your 9 protons, which are positive, plus, but after accepting 1 electron, fluorine doesn't have, 9 electrons, 1 to 10, but they are negative. If you do the math, that's the charge of a stable atom of fluorine, charge of a stable atom of fluorine after accepting 1 electron. And we call this a negative ion or an ion. You see that when you are moving within the nonmetals, you here in the nitrogen, you're going to start the non-metal part. Nitrogen was accepting 3. But if you look over here at the periodic table, nitrogen is going to accept 3. But if you move to the right, oxygen is going to accept 2. Fluorine is going to accept 1. And if you look at the period, at the group number, it's giving you a hint. Just remember, the tendency is to reach stability. How do you reach stability? By reaching, the electron configuration of noble gases. How many? All the elements that are in group 15, how many more electrons do they need to reach 18? 3. So they're going to be accepting 3. Group 16, how many more electrons do they need to reach 18? 2, negative 2, because they are accepting that. See that? And over here, how many? They need 1 more. They are accepting 1 more. But as you can see, from group 15 all the way to group 18, the amount of electrons that the nonmetals are gaining start going down. That is why, even though the tendency within the metals is for the ionic radius to decrease, once that you have reached the non-metal part of the periodic table, the ionic radius is going to start increasing, increasing to decrease 1 more time, Like within the non-metals, they're going to start increasing, and then they're going to start decreasing 1 more time. Mirame, what's going to happen in the group? Since when you go down a group, you are increasing the level of energy, it doesn't matter. It doesn't matter how many electrons you're losing or gaining, it still is going to increase because you have more level of energy. Okay, now we're going to continue with the ionization energy. And according to your book, the ionization energy is going to be defined as the energy required to remove an electron from the gaseous atom. Rama, what does that mean? I don't know. Very confusing for me. Ionization energy is the energy required to remove electrons that are located in the last level of energy. Okay, so is energy needed just to remove those electrons in the last level of energy. Now, what's going to happen across the period? That's why you have to memorize all the periodic trends. When you were moving across the period, the atomic radius was decreasing because the nucleus was able to pull that electron cloud towards the nucleus or towards the center of the atom, meaning that the nucleus has control over the electrons that are in the last level of energy. So if your parents, they have control over you, a person can come to your house and, kidnap you. Impossible. The same is going to happen with the electrons. So in a period, since the atomic radius is decreasing and the nucleus has total control of the electrons that are in the last level of energy, the ionization energy is increasing across the period. So it's going to be more difficult just to steal those electrons that are in the last level of energy. Okay? Which makes sense because I was explaining to you that the tendency of the nonmetal is just to accept. Okay? No one can steal from them. From the nonmetals, no one can steal from them because it's going to be very hard just to get the last electrons that are in the last level of energy because of the control that the nucleus has over those electrons. On the other hand, see, here in the group, we have a problem that as we are going down, the level of energy, they are increasing. Okay? Do you think that the nucleus has control, like total control over all those electrons in the last level of energy? It's impossible, especially when you're moving down. When you go from, period 1 all the way through period 7, you go from 1 level of energy all the way through 7 level of energy. See? 7 level of energy. Over here, the nucleus still has control over the electrons. But when you have 7 level of energy, it's very difficult to control the electrons that you have in the last level of energy. And that's why when you are moving down a group, okay, the ionization energy, the tendency of the ionization energy is just to decrease. And this trend is super simple. The last trend that we're going to analyze over here is electronegativity, which is the ability of an element to attract electrons in a chemical bond. To use to attract electrons in a chemical bond. In other words, it's the ability to accept electrons. I mean, Rama, we're so confused right now because you were explaining at the beginning that the metals, they do not attract electrons. They lose electrons. While the non-metals, they're accepting them. So, Ms. Ramos, our ability to accept electrons, metals, they're going to be able to accept electrons. The answer is no. And that's why when you're moving across the period, electronegativity is going to increase. Okay? Because the metals they're losing, the non-metals are accepting. Okay? And between a metal and a non-metal, the non-metal is going to have like a greatest electronegativity. Why? Because of this. Because the tendency of the metal is to lose, while the tendency of the non-metal is to gain electrons. Okay? Now, what's going to happen? What's going to happen in a group? See? The electronegativity in a group is going to decrease. Okay? It's going to decrease because even though the metals, they are not accepting electrons, a lithium atom has the more ability to steal 1 electrons than, a francium cesium atom. And it's because of the distance. It's all because of the distance in the ionic radius and the distance in the atomic radius. Okay? So this is super simple. Metals, when you are comparing metals, the farther that they are, in the like in periods. So the further that they are down, the less that is going to be the electronegativity. Now, but when you are comparing metals and non-metals, the non-metal always they're gonna have like a greater electronegativity than the metals because of the tendency of the metal just to lose electrons. Now, Ms. Ramos, what do we have to learn all of this? Because you're gonna be solving problems like the ones that are described over here. And when you have a question or problem like that, your first step is just to find the location of the element in the periodic table. Okay, Ms. Ramos? Are you gonna give us a periodic table? But of course that I'm gonna give you a periodic table. And if I don't give you a periodic table, I'm gonna give you the atomic number. Can you find the position of the element if the atomic number is given? I'm gonna leave that question over there because I don't want to answer that. Period 2. Okay, then I have over here aluminum, which is, see, in group 13, period 3. Period 3. And then you have oxygen over here that is in group 16. Okay, period 2. And we have potassium. Potassium that is in group 1. Group 1 in period 4. Oh, mi ramo, but now we have 4 different elements que they are located in, see, different groups, different periods. How am I going to analyze this? How am I going to analyze? By looking at the location. The period number is giving you what? The number of levels of energy. See that? And what is the atomic radius? The distance between the nucleus to the last level of energy. That's the atomic radius. Nucleus to the last level of energy. So if you analyze the numbers that you have over here, which is the one with more level of energy? See, 4 levels, that's potassium. That's the one with the highest atomic radius. So I'm gonna put potassium over here. After that, what is the next one? 3 level of energy. That is aluminum. And then I have to move to oxygen and carbon. Oh, Ms. Ramos, but I have a problem. They are in the same period. But you learn in this video that when you're moving from left all the way to right, what's gonna happen to the atomic radius? It's gonna decrease. So between oxygen and carbon, see, what is the one with the smallest one? So you have oxygen, which is the smallest one, and then you have carbon. And that's how you are organizing all the elements by increasing atomic radius. And that's the reasoning that I want you to make when you're solving problems like this. Let's look at number 2. Okay. Saying your first step. What is your first step? Your first step is to look at the position. Oh, Ms. Ramos, but what's going to happen if I don't have the name or I don't have a periodic table? If I give you the atomic number, you're going to be able to find the position. And that's why before teaching you this, I was teaching you electron configuration. Group, sulfur is in group 16, period, 1 period. I have a periodic table in front of me. That's what I'm doing this so fast. But let's say that I don't have a periodic table and I have the atomic number. I will write the electron configuration and I will find the position. Oxygen, We know that oxygen is, a ver, in group what? Group 16. Y aquí es group 16, no? Group 16. What period is in period 2? Period 2. Then I have neon, which is a noble gas. Neon is in group 18. What period? Period 2. Period 2. Y then I have aluminum. Aluminum, which is in group 13. Period 3. Okay, one more time in Ramos. Okay, you have a bunch of elements here in different periods, elements here that are in different groups. But now is when you have to use your critical thinking skills. What is electronegativity? Ability to steal. This is Ms. Ramos using her words. Steal electrons just to reach, okay, the noble gas configuration. And what is the noble gas configuration? Having A electrons in the last level of energy. Over here you have neon. Okay, neon is a noble gas. They are inert. They do not react. And why they do not react? Because they already have the A electrons in the last level of energy. Neon has any electronegativity. He needs that just to steal electron and to reach stability. The answer is no. So from the 4 that you have over here, the one with the lowest one, that's neon. The one with the lowest one, that's neon. Okay? Then you have to analyze the other 3 that are left. Non-metal, and then you have a metal. And I was explaining to you that the tendency of the metal is just to lose electron, not to accept one. So immediately, aluminum is the one that is coming after neon, because the tendency of the metal is just to lose electrons. Okay? They are not accepting electrons. They are not stealing. They are letting go. And now you have sulfur and oxygen. One is in period 3. The other one is in period 2. But they are in the same group. In the same group. So you were learning from this presentation that as you're going down, electronegativity is going down too. So between oxygen and sulfur, which one has less electronegativity? Sulfur. And then you have oxygen. See? Neon, because it's a noble gas, no electronegativity. Electronegativity equal to 0, because he doesn't need to steal. Aluminum, because it's a metal. And the metal, the tendency of the metal is just to accept electrons. They're not stealing electrons. Then you're going to look at the 2 nonmetals that are left over there. See that? They are in the same group. Now, as you go down a group, electronegativity is going to decrease, and then you organize them in there. With this information, guys, this information, you're going to be able to complete your homework. Okay? So you sit down at home, you watch this video as many times as needed, and then you complete the homework. Okay? You have any question, you write it down, and then you ask me when you come back.